Application of FACT devices for optimal transmission line loading. Abstract. The study involves identification of underutilized transmission lines in power system and with the help of FACT devices improve its loading characteristics, slightly below their thermal limit, and also study the possibility of using existing facil ities in substations, shunt compensator, i.e. capacitors banks to be transformed to series compensators when needed by adopting proper switching methods and control. The simulation involves observing the behavior of simple double-circuit transmission line having different line parameters in normal and compensated modes. The simulation is done in MATLAB. Index terms: zero voltage switching, ZVS, zero current switching, fundamental frequency modulation, Thyristor switched series capacitor, Tssc, switching loss reduction, reactive power compensation, fast Fourier transform, FFT. Introduction. Power grids play vital role in nation development. As we are a developing nation, the energy requirement always outnumber the energy availability. As energy requirement is a key factor for nation's growth, we can't avoid the need for expanding grids' power handling capabilities and circuit lengths to meet the rising demands across the length and breadth of the nation. As a result, the grid become more and more complex, often creating bottlenecks in power flow. These conditions may occur as a result of simultaneous tripping of multiple numbers of transmission lines, or due to change in normal grid connections to meet exigencies, or due to maintenance work done in transmission lines. This results in partial power outage or in some case blackout. We can tackle this problem by expanding grids, but it is often very costly and is not preferred. During this kind of situation, some transmission lines may get overloaded. Some double circuit lines may undergo uneven load sharing. All these factors affect the power transmission capability adversely. This study aims to find a solution to improve the line loading capability by using existing capacitor banks provided in substations and using these as Tssc when needed. The development of power electronics has led to many major advancements and breakthroughs in almost all areas of electrical engineering and industry. FACT devices are one such advancement. Nowadays we are using FACT, flexible AC transmission, devices for many power transmission applications, due its capability in solving many complicated issues in power systems such as stability, harmonics, distributed generation, wind energy integration, etc. Even though there are conventional methods for solving some of the issues, these methods' efficiency compared with FACT devices are very low. In this study we are considering a transmission line loading problem occurring due to variation in line parameters over different circuit length. Conventional methods to tackle this uneven loading problem is to vary the line parameter, to introduce regulating transformers 3, etc. The transmission line's uneven loading is a serious issue, leading to power outage, excess thermal stress of existing lines, in turn leading towards damage of conductors. In severe cases, partial blackout also occurs. Our attempt is find a solution to this problem by using existing devices in substations along with static switches. After identifying the lines that are loaded unevenly at the feeding substation end, we can introduce our FACT device and modify the power flow as required. As we know, substations are equipped with capacitor banks for power factor correction and voltage profile improvement. We can utilize these capacitor strings as compensating device when needed. We are actually turning this capacitor as Tssc, Thyristor switched series capacitor, FACT device, and using them as a series compensator. 2. Application of FACT device for optimal transmission line loading. By using Tssc, Thyristor switched series capacitor, we are actually offsetting lines' inductive reactance, thereby reducing overall line impedance. The variation in line parameters is a function of conductor length. The line parameters are resistance, inductance, and capacitance. These variables have fixed value rated as resistance/inductance/capacitance per unit length for a particular conductor. Depending on the excitation voltage levels and power handling capability, we choose our conductor. Once we choose the conductor, the parameter are known and is a function of length. All these parameters are proportional to length. Fig. 1. Overview of major FACT devices. Usually power lines are double circuit lines, single circuit and multi-circuit lines are also possible. Here we are considering a double circuit line with different circuit lengths, and line is modeled as series lumped resistance and reactance. The shunt effect is neglected, so our line variables are inductance and resistance. A FACT devices overview. The development of FACT devices has started with the growing capabilities of power electronic components. Devices for high power levels have been made available in converters for high and even highest voltage levels. The overall starting points are network elements influencing the reactive power or the impedance of a part of the power system. For the FACT side, the taxonomy in terms of dynamic and static needs some explanation. For The term dynamic is used to express the fast controllability of fax devices provided by the power electronics. This is one of the main differentiation factors from the conventional devices. The term static means that the devices have no moving parts like mechanical switches to perform the dynamic controllability. Therefore most of the fax devices can equally be static and dynamic. The left column in figure contains the conventional devices build out of fixed or mechanically switchable components like resistance, inductance, or capacitance together with transformers. The fax devices contain these elements as well but use additional power electronic valves or converters to switch the elements in smaller steps or with switching patterns within a cycle of the alternating current. The left column of fax devices uses Thyristor valves or converters. These valves or converters are well known since several years. Fig 2. Ideal series compensator connected in the middle of transmission line. B. Applications of FAC devices and compensation methods. Flexible AC transmission systems, called FACs, got in the recent years a well-known term for higher controllability in power systems by means of power electronic devices. Several FACs devices have been introduced for various applications worldwide. A number of new types of devices are in the stage of being introduced in practice. Even more concepts of configurations of fax devices are discussed in research and literature. In most of the applications the controllability 5 is used to avoid cost-intensive or landscape-requiring extensions of power systems, for instance like upgrades or additions of substations and power lines. Fax devices provide a better adaptation to varying operational conditions and improve the usage of existing installations. The basic applications of fax devices are power flow control, increase of transmission capability, voltage control, reactive power compensation, stability improvement, power quality improvement, power conditioning, flicker mitigation, interconnection of renewable and distributed generation and storages. In all applications the practical requirements, needs and benefits have to be considered carefully to justify the investment into a complex new device. The usage of lines for active power transmission should be ideally up to the thermal limits. Voltage and stability limits shall be shifted with the means of the several different fax devices. It can be seen that with growing line length, the opportunity for fax devices gets more and more important. The influence of fax devices is achieved through switched or controlled shunt compensation, series compensation, or phase shift control. The devices work electrically as fast current, voltage or impedance controllers. The power electronic allows very short reaction times down to far below 1 second. The ideal series compensator 6 is modeled by a voltage source for which the phasor is Vc, connected in the middle of a lossless transmission line. The current flowing through the transmission line is given by I equals VSR/Vc /JXL VSR equals VSR/VR. If the ideal series compensator voltage is generated in Fig 3. Tssc implementation and performance analysis. Such a way that its phasor Vc is in quadrature with line current I, this series compensator does not supply neither absorb active power. As previously discussed, power at the series source is only reactive and the voltage source may, in this particular case, be replaced by capacitive or inductive equivalent impedance. The equivalent impedance would then given by ZEC equals XL, 1 plus S, where S equals X comp/XL, 0 equals S equals 1, is the compensation factor and X comp is the series equivalent compensation reactance, negative if capacitive and positive if inductive. In this case the compensation voltage is given by Vc equals IL ZEC and the transmitted power is equal to PS equals V2/XL, 1S. Sin D equation shows that the transmitted power can be considerably increased by series compensation, choosing a proper compensation factor S. The reactive power at the series source is given by QCS equals 2V2/X1S/1S, 2, 1 cost. Tssc implementation and performance analysis. Figure 3 shows the Thyristor switched series capacitor, Tssc. In this device, the thyristors should be kept untriggered so as to connect the capacitors in series with the transmission line 7. If the thyristors are turned on, the capacitor is bypassed. Thyristors turn on must be at a zero voltage condition, ZVS, as it occurs in the case of the Tssc, to avoid current spikes in the switches. An example of an application based on this concept is presented in. This compensation system has the advantage of being very simple. However, it does not allow continuous control. If the connection/disconnection of the capacitors is to be made at sporadic switching, no harmonic problem occurs. Depending on the frequency the thyristors are switched, harmonic or subharmonics may appear. In this arrangement, it is interesting to choose the value of the capacitors in such a way that many different combinations can be achieved. 3 simulation models and results. A simulation parameters. The simulation parameters using in figure 4 is given below. It consists of the behavior of compensated and uncompensated lines. This simulation basically consists of 2 transmission lines. One with Tssc and other without Tssc. Source voltage, 100 kV line 1, compensated 6.25 20 K equals 125 mH, 39.26 ohm line 2, 6.25 10 K equals 62.5 mH, 19.6 ohm capacitance, 70 UF, XC equals 45.47 ohm load 1, 50 MW load 2, 3 MW. The Tssc subsystem is represented in figure 5. And its simulation parameters are given below. Pulse generator Ts equals 5s, 50%, duty ratio, 2.5 milliseconds delay. The basic objective of the simulation is to demonstrate the effectiveness of the compensation technique that we discussed in the simulation. A double circuit transmission line with a source and some loads, as specified in the above parameter section. These are used to demonstrate the compensation technique. The transmission lines are modeled as RL branch, neglecting the effect of shunt capacitance, and the equivalent impedance is made higher for one line and lower for other, in order to incorporate the effect of length over impedance of the line. The line with higher impedance is incorporated with our Tssc block to provide compensation as required. Measurements are provided for currents in both lines, and a trigger is provided for the Tssc block, which helps to engage the Tssc block as required. The effect on power delivered by each transmission is observed with and without. IG. 5 Tssc subsystem. Compensation and simulation is done for various performance parameters. For conclusion from our simulation model, it is observed that the line current in compensated line increased about 50%, thus relieving the adjacent line current by about 24%. From power system point of view now, the compensated system as whole can handle more power without overloading individual lines. From the simulation it is clear that using Tssc partially offsets the inductive reactance and improves line loading characteristics, thereby enabling the power transfer more efficiently.